Good afternoon, everybody. Apologies for the slightly late start. We're streaming, we're recording, we're doing all sorts of tech things, so it just took a little while just to get everything working. First of all, a very warm welcome to you all. Thanks very much for coming to this launch of the 2022-23 Northwest Science Network program. First of all, let me introduce myself. My name's Pete Ellis. Up at the top there, this laser point is not very strong. Just to tell you a little bit about myself, I think can you still hear me okay? Yeah, there we go. I'll keep very, very still. So I'm actually a professor of material science at the University of Oxford, and I lead a research group that uses very powerful electron microscopes to look at atoms and see how atoms are arranged in materials and how they bond together in materials, and help use that understanding to develop new materials. But I'm also a tutorial fellow, so I do a lot of teaching as well at the university. But my another job that I do is I'm the academic lead on this thing we call the Northwest Science Network. And this is the launch event of this year's program. So what we're just going to do this afternoon is I'm going to tell you a little bit about the network to start with, and then we've got three more sciencey talks from three what we call more early career researchers, telling you a little bit about the sort of research that they're doing. That'll take us through to about 3 o'clock or so. And then we're going to go through to the sports hall, where you can actually spend time talking to us. We've got some other scientists as well who come from some other universities to talk to. And there's some demonstrations you can get your hands on, like doing some real experiments and so on. So that's what's going to happen from 3 o'clock. So let's talk a little bit about why have a whole load of us brave the M6 from Oxford. People come across from Bangor, various places to come and talk to you this afternoon. Well, there's a very simple reason. We've got problems. We've basically got energy issues. A lot of the energy we're using often generates carbon dioxide. We know that carbon dioxide leads to warming and all the problems that that's causing with weather and so on. So we need to worry a lot about energy. Many renewable energy sources are intermittent, such as wind or tide or solar, as you're very aware. So you can imagine that one of the challenges that we face is the ability to store energy. We have to store energy to make use of renewables. And also, if we can store energy, we can have like electric cars and so on. So batteries are very important in my department. We do a lot of work on batteries. Batteries have progressed a lot over the last 2 years. This is the source of capacity increase in lithium-ion batteries, which are the sort of batteries you have in your phone or your laptop or something like this. The capacity here has gone up hugely over the last few years. Costs have come down dramatically. We've made great progress with batteries, but we need to do better. We want cars that can have ranges of, say, 400 miles. We need better batteries. And also, batteries have some problems. Sometimes they catch fire. You've seen maybe YouTube videos of laptops that have caught fire due to the short-circuiting and overheating. So there's a lot we need to do, a lot of challenges, not only in these sorts of materials, but also thinking about healthcare, environmental issues, and so on. And so if you then think about it, if these are the challenges that we really face as a civilization, what we really need are scientists, right? We need scientists. We need people like you, you're the future, to come and join with us and work with us and do science to solve some of these problems. And that's essentially what the network is about. We want to use the resources we have as higher education institutions to encourage you to be ambitious and to think widely about how you can contribute and how you can do science with us. But let's talk a little bit more about what the network is actually aiming to do. We aim to enhance subject knowledge in STEM subjects. STEM stands for science, technology, engineering, maths and medicine. And so we have all sorts of activities, which I'll tell you about in a minute, which will give you more knowledge about subjects and what the research frontiers are, where we do research in different areas. We want to give you a chance to learn more science, greater ability, and also give you more confidence to explore your interest in science, be confident in talking to people like me and other research scientists, and ask questions, and really be curious about science, and learn more about science. We want to raise the profile of non-A-level subjects. We know that a lot of people tend to apply the university courses in the subjects they're studying for A-level, but there's a whole wonderful range of different subjects that you can study at university. And don't worry about this graph, you're not going to be able to see this, but this is a bit of a plot of courses that we have, say, in my own university at Oxford versus the competitiveness, the number of how competitive they are a little bit less competitive, but often people aren't aware of these sorts of subjects. We want to raise awareness of non-A-level subjects. And alongside that, think about thoughtful course selection. What is it you really want to study? Do you want to do genetics? Yeah. Do you want to do, marine oceanography, as we're going to hear about a little bit later, and so on. So these are the sorts of things we want you to think about. We want to raise your aspiration and ambition. Where's the best place you can think of applying to study the thing you're interested in? Or where's the place that's got a really good department in a particular area that you might be interested in? You know, don't just think what's the uni down the road, but where's a really good place to study this? And also work with schools and communities generally to promote the study of science. So that's what we're aiming to do with the network. How it actually works, we essentially resource it, my own college in Oxford. We work with 3 hub schools, Cheshire College South West here, Zaverian Sixth Form College and Blackburn College. They act as hubs, which then interact with other schools in their region to encourage schools from across the region to engage in our activities. And we provide the academic resources and leadership working with our partner higher education institutions. Just to give you a bit of a sense of the programme, it's aimed primarily at Year 12 students, but others are always welcome, particularly in some of the more open sessions, such as the lectures. And we're going to start introducing earlier stage activities this year. It starts with the October launch lecture and STEM fair. That's what this is. So that's what you're at. There's going to be a series of twilight lectures coming up, which are afternoon lectures from scientists talking about their research, and they're going to be held across the 3 hubs. We have university interview workshops for those who are thinking of applying to university to interview. We can help with that. We're going to have laboratory visits. We're going to go to the Darsbury laboratory. We're going to go to other laboratories in the region. We've got an Easter maths workshop where we demonstrate the importance of maths across a wide range of science. We show that if you want to try and treat cancer, you've got to know some good maths. And so we use things like that to illustrate how important maths can be. And it finishes with a summer school that we hold down at Oxford. Of course, there's a huge amount of fun, a lot of fun. We have up to 30 students coming on that. We do tutorials, we do self-study work, there's lectures, hands-on laboratory sessions, poster presentation, group work. Got students from a wide range of schools across the Northwest coming to that. Places are limited, we have an application process, and for those students who are engaged in other things during the year, you get preferential treatment in the application process. And it may well involve a problem-solving exercise this year as well. And actually, one of the things that Fiona, thanks again to Fiona Massey for doing all the logistics today, for setting this up. Fiona reminded me to tell you that when you are doing activities like this, write down what you've done, because then when you are applying to uni, really go to your personal statement, talk about what you've actually done in terms of the Northwest Science Network. So keep note of those activities that you've been on, and when you're applying to us for events, you can also note down what other Northwest Science Network events you've been to. So at this point, I'm going to just shut up. There is a website, it's got quite a long URL, but we have little cards that we've printed off, which you can collect at the end, which have a QR code. Emma's got them right here. And you can click, it's got a QR code, you can then register with us, and you'll be informed of all the events coming up throughout the year. Right, I'm going to shut up now. I'm going to hand over to the early career researchers to tell us a little bit about their research. And first up is Matt Haynes, who's from the Department of Chemistry. Matt's just finishing his second year as his PhD, so he's really been after your undergraduate, learning to become an independent researcher. And Matt's going to tell us a little bit about his work. So Matt, it's over to you. Before I hand over to Matt, anybody got any urgent questions about the network? I'm going to be around doing the STEM fair afterwards. You can talk to me informally as well. Anybody need to know anything at this stage? No, you're all good. Fantastic. Matt, it's over to you.
I promise I've got more than this. Give me a hand.
Yeah, I think
Get myself.
Darling, this is running down the stairs.
Right, good afternoon everyone. Thanks Pete for the introduction. My name is Matt and I'm a PhD student at the University of Oxford. So this afternoon I'm going to share some of my research into sustainable plastics with you. But first I just thought I'd talk a bit about how I ended up putting myself through a chemistry PhD. So I grew up just over the border, over the Pennines in Sheffield, where I went to a state school called King Edward's. At this point, like most people, I didn't have any idea what I wanted to do at the stage of my life that I'm now at. But my school did have an after-school STEM club, and I'd always been kind of interested in science, so I joined that. I got to do some cool experiments, and that was maybe when the seed got planted for me to want to do more sort of practical science down the line. And I then was able to volunteer in one of the later years. I then moved on to my school's upper school to do my GCSEs. I think, like most GCSEs, I kind of found the science courses to be a bit of a slog, but I got through them. I had some really good teachers, which helped a lot. And when it came to choosing my A-levels, obviously that put me off. I did chemistry and biology, and then I also did further maths and history. Those were actually my two sort of best and favourite subjects when I came to choosing my A-levels. For anyone that is thinking about what A-levels they might want to do down the line, I would just go with whatever you're most interested in. That's what I did, and it worked out quite well for me in the end. So yeah, I did history just for 1 year. 1 year of writing essays about monasteries was kind of enough for me, but so I sacked it off after that. But it was really good in terms of developing my writing skills, which was helpful for writing my personal statement and for plenty of other stuff that I've done since. So it's definitely worth doing. I then really enjoyed all of my other 3 A-levels. When I started to think about applying to uni, my first thought was maths, because that had often been my best subject while I was going through school. But I went to a few sort of extracurricular maths sessions that were run by Sheffield University, and the kind of maths they were showing off there wasn't the kind that I was so interested in, and I was more looking to do some practical lab-based science as well, I think. So when I then kept looking at unis, I started going to open days, which I found to be really helpful for a few reasons. I'd really recommend it. The first is that in terms of choosing where you want to live, you get to decide if you want to go to a campus uni, if you'd rather go to like a small university town, or if you like more like a big city. And then secondly, in terms of choosing your course, you get to go to lots of different departments and see what they have to offer. And as Pete said, you might come across some courses that you haven't done at school. So in my case, I became exposed to biochemistry by doing this. So obviously there's bits of that in both chemistry and biology, but it was looking around unis that really put me onto that. And so yeah, when I was starting to actually narrow down my choices, it came to biochemistry and chemistry. And in the end, I went for some chemistry courses. I applied for that at Manchester and 2 unis in London. But on top of that, I applied for some natural sciences courses at Durham and Cambridge. And the idea of a natural sciences course is that you're not narrowed down to just one subject at the start of uni, and you can do a few different ones and then choose why you're there. And so when my offers came through, my indecisiveness kind of prevailed, and I went for the natural sciences courses. And in the end, I ended up going to Cambridge to do a natural sciences degree. I just mentioned before I move on to that, in terms of extracurricular stuff while I was applying, a useful thing I found to do was just to read some books about whatever subject you're applying for. What the admissions people are looking for is just that you have a real interest in the subject that you're wanting to do, and just doing some stuff outside school is a great way of demonstrating that, and it will definitely expand your knowledge as well and give you things to talk about in interviews. Just make sure you actually read the books. So yeah, then moved on to Cambridge. I had a really good time, made loads of really good friends. If you can stand the drinking water in the south, it's a really nice place to live. But yeah, it was hard work, but it was really rewarding as well. I had plenty of time still for things like sport and then going out, everything like that. The same is obviously true for any other uni. I had friends from school that went to unis all over the country and all had a great time and all have good jobs now. So yeah, if you find a course in a city or a town that works for you, just go for it and you'll probably have a good time. So yeah, my first year of natural sciences, I was doing chemistry, cell biology, a maths course, and then physics. I didn't do physics at A level, so that was a bit of an interesting decision, which I probably regret it now because I found it pretty tough. But it did help me down the line with some of my chemistry, so it's still worth doing. By the end of second year, in which I did biochemistry and chemistry, I kind of figured out that chemistry was the one for me. Some of the biochemistry style labs I didn't enjoy quite as much, and I also had to memorize a lot of things and write some essays, which some people really enjoyed, but I prefer chemistry. So in the summer of 2018, I managed to get myself an internship at a small commercial lab in Sheffield. This just involved making some new compounds, but it was kind of the first time I got to do more of like a 9-to-5 job in a lab. And I found that I really enjoyed it and that it kind of worked for me. So this was the first time that I maybe thought about carrying on with science after my degree. So yeah, carried on through my third year. And at this point, you kind of have to make your mind up about what kind of chemistry you want to specialise in. Because moving into fourth year, you do a master's, which involves a big research project. And that is in a research group like Heats that does a quite specific kind of science. So originally, when I was deciding what I wanted to do, I was thinking about organic chemistry, which is maybe what you guys might know more about. It involves things like drug development. But in the end, I ended up doing what's called inorganic chemistry instead, which involves pretty much anything else from the periodic table. In this case, it was some phosphorus chemistry. I won't talk to you today about that work, but I really enjoyed the project itself. I kind of got the bug for doing research on a daily basis. Making new molecules was something I found really rewarding, and I really enjoyed the group I was working in. I had lots of really good mates that I still talk to now. So yeah, I kind of made up my mind I wanted to keep going with research and decided to apply for some PhDs based on that. So for anyone that doesn't know, a PhD essentially just involves doing research, learning about new science, and then towards the end, you don't have to do any exams or anything, but you do have to write a big thesis, which you then have to sort of defend to a few academics. But I've not reached that point yet. And so when I got to the end of my time at Cambridge, I ended up moving over to Oxford to do an inorganic chemistry PhD. And so yeah, that is what I'll spend the rest of the talk talking about. So as Pete mentioned, the main reason most of us are scientists is that there's a lot of problems in the world right now. And one of the big ones is plastics. So I'm sure we all know plastics are incredibly useful and fairly irreplaceable in modern society. There won't be anyone in the audience right now that doesn't have something containing plastic on them. However, as we're going to hear more about in a bit, there's a lot of issues with how we currently produce, use and dispose of our plastics. So the first one is that all of the raw materials we use to produce plastics come from fossil fuels. This is bad for two reasons. One, it means we're continually digging them up, burning them, and producing greenhouse gases. And the second is that they're non-renewable, so eventually they're going to run out. Secondly, when we're done with these useful plastic products, they all end up either being incinerated, which produces more greenhouse gases, or they end up polluting natural habitats. So overall, we have this linear flow of non-renewable resources down to waste. And obviously this can't keep going forever. It's causing a huge amount of issues in the environment. And it's something that a lot of scientists are working on right now to try and fix. So one thing we can obviously do is try to recycle. I'm sure most people do that at home. But at the minute, I think less than 10% of all plastic that is used actually gets recycled. So what we actually want to do is develop new plastics that are more sustainable in general. So to do this, what we want are plastics that have what's called a closed loop life cycle. And this means that they're both sort of sourced from renewable resources and that they are biodegradable. So at the end of their life, even if they end up polluting a natural habitat, sort of microorganisms that are present can degrade them and convert them back into carbon dioxide. So obviously that looks quite similar to what was happening before with the incinerator. However, in this case, plants can kind of do the work for us and turn these greenhouse gases back into plants pretty quickly, much faster than you could ever regenerate oil reserves. And this can create plants like sugar beets or corn, and we can ferment these to turn them into renewable feedstocks. And in the case of my chemistry, these are known as monomers, and monomers are the building blocks which we use to join together to make longer chain molecules called polymers, and it's polymers that are what make up plastic. So one biodegradable polymer that has become useful is called polylactide. This is fully biodegradable and has been applied to things like packaging and biomedical instruments. And this is a polyester. We call it that because of these oxygen atoms that are in there, and this is what makes it easier to break down. So yeah, this all looks good on paper, but as you might have guessed from the fact that none of us actually use too many biodegradable plastics right now, there's still quite a lot of issues associated with doing chemistry, but that's where I come in. So I'm trying to close this loop to make this polymerization work. So how does this actually work? We do lactide polymerization through a process called ring opening polymerization. So we saw on the previous slide that lactide has a sort of ring-shaped structure, and we can think of that almost as a piece of string that's been tied together into a loop. And so what we can do is, if we're able to untie that loop, we then have lots of shorter lengths of string, which we can tie together to make a much longer chain. And so that gives us our polymer. So in chemistry terms, what we have to do is take these ring-shaped monomers, break the carbon-oxygen bonds that you can see within the rings, and then form new carbon-oxygen bonds between the short strands to make a much longer chain. So again, this all sounds good on paper, but in order to actually untie our strings, we need a pair of hands, and that's kind of where I come in. So I work with catalysts, and often what we need to do to make a process like this work is to use a catalyst, which often contains a metal. So as you may or may not remember from GCSE, catalysts increase the rate of a reaction without being used themselves, so that kind of works with the hands metaphor. In terms of sustainable chemistry, which is what I'm interested in, they're really good at making reactions greener because they reduce energy consumption. So other things you can do to increase the rate of a reaction are things like high temperatures or high pressures, but things like that also consume a lot of energy. So if we can reduce the need for them by using a catalyst, that's great, and it makes everything more sustainable overall. And yeah, for this reason, catalysts are already used on a huge scale worldwide. The current market for global catalysts is valued at $35.5 billion. I was going to say how much that was in pounds, but it's probably changed since I started talking.
About 35.
And yeah, just in terms of the chemistry I do, the catalyst is also very important in controlling what the polymer we make looks like. So one of the main things is how many monomers we're able to join together and how long the final polymer is as a result. And so that affects properties of the plastic, such as how rigid or bendy it is, things like that. And then finally, at the minute, a lot of the catalysts that are used by industry are actually based on metals that are quite toxic or that are very rare and therefore very expensive. And so obviously this kind of counteracts any sustainable credentials. You might be making a biodegradable polymer, but if you're pumping like toxic heavy metals into the environment, you're not really doing much good. So we need the catalyst to be sustainable too. And so with my work, we've chosen some metals that kind of adhere to that. And so the metals I work with are magnesium and calcium, which you've probably heard of, and then strontium and barium, which maybe you haven't. But these are all in groups 2 of the periodic table, which means they all have quite similar properties. The only difference is that as you go down the group, they tend to get bigger in size. So yeah, what do the catalysts I make actually look like? So this is my most sort of sciencey slide, but you can see from this molecule that's circled that we have a metal, which is N, and that would be one of these 4 metals on the side here. And then this is bonded to 2 nitrogen atoms, and that these are sort of bridged together by some carbon scaffolding. And what this does is it puts our metal in a more sort of defined environment, and this gives us some more control over the reactivity we want to do. And as you can see, this metal is also able to bond to a monomer of lactide. So this is almost as if our hands are picking up one of the small loops of string. What happens next is that something called a nucleophile is able to attack our ring, and this kind of helps us untie it and create our first short chain. And this, as you can see, opens up the ring. We have our nucleophile group, which is the X group in orange, but we've also broken that first carbon-oxygen bond. The next thing we need to do is start linking these open chain monomers together. And what we actually find is that once we've opened one of these up, it can then itself act as a nucleophile. So the next monomer will come along and get picked up by the catalyst. So our hands will go and pick up another loop of string. And then one of the shorter chains will come and attack and we'll link them together. And that's how we start to make our longer chain. And we end up with a polymer, which has the repeat unit that looks like this. And yeah, this can be as long as we want, as long as we keep adding one. So yeah, that's kind of it in terms of the science I do. This is what I'm aiming for, this catalytic cycle. This is still hypothetical as yet. The work I mainly try to do is actually making the catalyst, which is often the hard bit, and then doing things like testing which metal is the best and which atoms we want to control our reactions. But I thought I'd talk a bit next about just sort of what I actually do day to day in the lab. So this is me in my lab coat with my gloves on, back when COVID was still having us wearing masks as well. But we're all very used to PPE anyway in the chemistry lab. And then one of the things I do that I think kind of reminds me that my work is a little bit different to most jobs is that I normally start my day by going to collect a big bucket of liquid nitrogen from this tank, as we have some equipment that needs to be kept very cold at all times while we use it. And yeah, this is kind of one of the perks of the job in the summer, especially with the summer we've just had. This big bucket gives off a lot of cold, which helps keep us cool. And then in terms of the actual work I do, most of the chemistry I do is called air sensitive, which means the molecules I make actually decompose if you expose them to the atmosphere because they react really quickly with things like water or oxygen. So you might think that sounds really pointless because we're obviously surrounded by water and oxygen all the time. But over the years, chemists have developed some clever methods to protect molecules like these. And we do this because their high reactivity means they can be very useful for things like catalysis because as they are so reactive, they can activate things like the monomers we were talking about before. So yeah, in terms of things I've made, you can see I've had this nice red compound, which is in this sealed glass tube, which keeps any air out. And then we have this sort of inlet on the side, which nitrogen is flowing through. So nitrogen is a nice unreactive gas, the same goes for argon, and the chemicals we make are stable in this context. However, we have to be very careful. The reactivity of these complexes can also make them quite flammable or even explosive. So if I dip a piece of filter paper in this nice red solution and then pull it out into the air, you can see from the scorch marks that it sort of spontaneously sets on fire. So we do have to be careful with this. It is a real risk. The St Andrews Chemistry Department did burn down a few years ago. So we're always safety first. We're trying to avoid that so I can actually get PhD. This is also an explosion that happened in the lab I did my master's in. Thankfully, the only thing that got hurt by this was the pride of the PhD whose fault it was. No one actually got hurt. But yeah, we do have to be careful. There's lots of forms to fill in if you cause something like this. So we always try to avoid it. One of the bits of kit we have to make our lives easier is called the glove box, which I just think looks like sort of the long lost sister of the long trousers from Wallace and Gromit. This is essentially just a big cupboard that is an airtight box full of nitrogen, and this lets us store our compounds that don't like normal air without having to worry about them breaking down when we come back the next day. And it has these gloves on the front which you can push in through, and that lets you do some fairly mundane work like weighing out chemicals or making samples for analysis that you normally do out on the bench if you did some slightly more straightforward chemistry. You can also have a bit of fun with the box if you want and get to do some hand gestures. I was also too embarrassed to ask about this, but if you've had a really bad day, you can get into the box to give you a hug. And then finally, the main reason I do this kind of chemistry is crystals. So there's three main reasons why these are important. The main is that they're really pretty, and I'm a child, and I like doing stuff like this. The second is that if you're able to grow crystals of your chemical, it means it's probably quite pure, which is something we always want. And then finally, there's this really cool technique called X-ray crystallography. And if you're able to grow some crystals of your compound, and it's a new compound, You can then fire a beam of X-rays at them. This gives you a diffraction pattern, which you can put through a computer, and essentially it gives you a nice 3D image of what the molecule that's formed into this crystal actually is. So if you're making something that's never been made before, this is really, really useful for seeing what you've got on your hands. So this is actually how they figured out the structure of DNA back in the 50s. My research isn't quite at that standard yet, but these are just a few pictures of some of the molecules I've made so far over the course of my PhD. You can see that there's one here, which has a magnesium atom in it. So this is one of the molecules I might be taking forward to use as a catalyst to turn some renewable monomers into biodegradable polymers. So yeah, that's pretty much all I've got to share with you guys today. If anyone's got any questions, feel free to ask at the end of the talks or in the hall afterwards. So yeah, that just leaves me to thank the organisers for letting me speak today, and to all of you guys for listening. I hope you found it.
Yeah, give Matt a round of applause. So as Matt said, this is all great. As Matt said, we'll probably take questions, maybe depending on the time. We might actually wait till we've gone into the STEM fair, actually, where Matt's going to be, so you can quiz Matt a little bit more if you want to, once we go through in there. But what we're going to do now is press on straight from the talks. And we've also got colleagues from the University of Bangor in North Wales who are going to give some talks now. And actually, the first I'm going to introduce is Jennifer Hewitt, who was actually here as a student and did A-levels here at Cheshire College. And she's going to be talking a little bit about her work in geological oceanography. So Jennifer, thanks so much indeed. There's the clicker for. No, that's the laser. That's the form. Oh.
I can hear myself. Wonderful. Hi, everyone. So yeah, my name is Jennifer Hewitt, and this is my face. Before I introduce myself fully, I'd like to get to know you guys. So a little show of hands, please. I understand we're a STEM kind of event, so I imagine some of you, at least, are interested in STEM. So can you raise your hands, anybody that's currently studying a STEM subject? Science, technology, engineering, maths, and medicine. Lots of you. Okay, keep those hands up. Anybody who thinks they'd like to continue STEM during higher education, go to uni maybe. Yeah. Okay. Well, all of you. Great. Wonderful. Okay. And then last one. Hands up if you guys know what on earth you want to do. At all. Oh, nice. Okay, I would fail at that question because little old me, right about this age, year 13, year 12, no idea. In fact, actually, I wanted to be a marine biologist. Definitely not one. So who am I? Here I am. So I'm an alumna. I studied here from 2016 to 2018. Had a really good time, met a lot of friends, colleagues, and that's why I'm here today, really. I'm a geological oceanographer. I did my first degree in geological oceanography at Bangor University. A lot of you are probably itching your heads about that. What is that? It's essentially, I study geology and oceanography at the same time. So, pretty complicated. I like to find the links between rocks and the oceans. There's the two different spheres that we have on our planet. There's the lithosphere, that's rocks. We've got the cryosphere, that's ice. We've got the oceans, we've got the atmosphere. So I like to make links between different things. And I'm also a postgraduate researcher at Bangor University. I'm very early on in my career. In fact, this is my 5th official day being a postgraduate researcher. So very new to this, but better. I'm doing my MSc Res, which is a Master's by Research. It's like a miniature PhD, so 1 year, pure research, very slow. And I'll tell you a little bit more about that in a minute. But my time here at South College, no, not South College, that's what it's called, it's first Cheshire College, South and West. I did geography, geology, and photography. Bit of a weird mix there with the photography. What was that about? Well, like I said, I wanted to be a marine biologist, and that was really cool when I was in school. And I got here, realised I'm so bad at biology. I have no idea what I'm about. So as you can see, there's more physical stuff than geology, whatever. The photography was a win. I started here doing biology, and I started here doing chemistry as well. Yes. Right. Yeah, I was bad. Hated it. So I changed, and I changed to photography. I thought, I'm here, I'm young, why not? So I did. And I enjoyed it. But that confused me a little bit. I didn't really know what I wanted to do even when I left. Let's see your results today. With my friend, who's also looking like a twin, skinny jeans and rips. Ooh, what a time. And yeah, once I left, I just still didn't know what I wanted to do. My friend was there, some of them did geology with me, they went off to do geology. I didn't. Not at first. Whilst I was here as well, I did open things, that was really fun. And it really built my personal statement on my CV, got me a bit confident when talking to people, still alone, but I also was on the student senate. I don't know if that's called that now. It's basically a student council. I went to meetings and said that the college was doing good, was doing badly, and I'm kind of continuing similar kind of things on at Bangor, as I'll tell you about in a few minutes. So yeah, let's be on results day. Left this place the last time, thought, oh my gosh, there is a world out there, and I don't know what I'm doing. And I didn't apply to university straight away. I went on a gap year. Very fun. I was doing a little wetsuit at the beach, with a boat, as my dog, moved around, travelled around with him for months. After that, I had a nice summer, settled down, worked at the pub. Very fun, but I didn't really like it. And it was during kind of this time, I should say I'm a bit of a wolf baby, hence the boats and the sea, everything like that. Around that time, I was boating, and I realised I really like the ocean, you know? It's pretty cool. I learned about it in geology, I learned about it in photography, not photography, geography. And yeah, I just thought, yeah, this is really cool. Kind of wanted to get into conservation at one point. I'm sure you've all watched it, David Attenborough. Thought, yeah, that's really cool. Thought, yeah, that's really cool. Found out that David Attenborough actually has an honorary degree from my university. So figurehead, we have them. I actually have a banner of him that you will see later if you go to the centre. So I thought maybe conservation. Maybe I'll tour the UK and look at universities that do ocean science, that do conservation, natural science. So I did. And I wrote a personal statement thinking that I'd be a conservationist. But I actually chose a generic course at Bangor. I chose a generic course called Ocean Science. And I chose that course because it's the only course at Bangor that actually had complete customizability. There were no compulsory modules. Everything was up to me. So I could choose whatever module I wanted. I could do geology one day, biology the next day. Didn't, I hate biology. Really bad at it. So, this should be. Whoa, that's not base. Bangor. So yes, I was on my generic ocean sciences degree. Loved it. Had a great first year. I did a lot of field work. I think this one, actually, the first year field trip. That's a place called Paris Mountain on Anglesey. Looks like a kind of crazy Martian landscape. Yeah, I really loved it. Then I realised, right at the end of my first year, I don't want to do this. Oh no, changed my mind again. It was really, really annoying. I went through so many course changes. Gave everyone a headache. Had a few meetings, and I realised geological oceanography was the right thing to do. I went from doing geology here to realising I don't want to do that. To coming back to geology. What mixed with the ocean? This is really cool. So this is some scientific equipment I deployed around this time last year. A few people, some of my lecturers are in that photo as well. That equipment is about £100,000 worth of equipment. And my lecturer in blue, he just sat on it as if it was a bench. Really cool. So that was recording in an estuary. The tide had gone out at that point, we're in the middle of an estuary. We deployed this equipment, left it there for a week. Real data collection, just out in the wild, and I got to write a report on that data. We were measuring the tides, and we were measuring how fast the tides came in and went out through the estuary. and also a bit of sediment transport, but for that we just dug a hole, buried some different sediment. It was a different colour than the sand, and then came back a week later, and went, oh, there's a colourful sand, it's moved. Basically what I do now. What else have we got? That's me up there, using an optical leveler. That's me on a salt marsh. I was measuring the level of the salt marsh to figure out if it was growing, shrinking. Interesting stuff. Also wrote a report on that. In the middle, that's me and my friend Caitlin, and we're back. We've just got off the boat in the same estuary, a bit further along. And in that little boat, we were depositing, throwing overboard, basically, some sample bottles. We're taking samples to measure the salinity and the temperature of the water. Just doing that, we can profile it. We're in an estuary. I don't know if you've learned about those in geography, but that's where a river meets the sea. So there's a lot of mixing involved there. Lots of different water properties. Salty at one end, brackish, kind of fresh at the other. We were mapping basically the estuary and its saltiness. Very interesting. And then the last one, it's just me up there. I'm somewhere in there. That's a lecture that I just had on the beach one day, because I'm an ocean scientist, I can do that. So I was just there taking notes. That's a LiDAR scan. You've heard of those. Drive past them on the road sometimes, scan things. Yeah, very cool. We're actually imaging the dunes at the beach, figure out how much the sediment has moved. So it's not just all wet rocks, sometimes they're dry. And then the last thing is this in the middle. And those are just some salt crystals. I went to table salt, basically. And if there's any geologists in the room, you know that sometimes crystals do grow in squares. They seem to right angles in nature. Don't speak to a geologist. Yeah, very exciting stuff. And I wouldn't have been able to do all of that unless I'd had those awkward phases. Unless I'd had those awkward moments where I thought, how do I do this? I wonder if that's really boring. Or I wouldn't have been able to do that without realising, yeah, I don't like what I'm doing. The best thing is that you have too late in your career to change your mind, basically. So yeah, it was a really good time. And I like to tell people about this. But so many pictures like this. And then there's my face again. So this is the other stuff I did at back then. It wasn't just studying and stressing out the admin with course changes. I did an internship. About that in a minute. I'm a STEM ambassador as well. So that has allowed me to come to places like this, do talks like this. Yeah, I can do outreach events, like I said. Open days, I work open days at the beginning. Got an open day at Bangor on Sunday. If anyone goes to that, comes down. Volunteering. You might see UNESCO, you probably recognize this thing. They are in charge of basically everything. You've got like World Heritage Sites and history. They've got global geoparks, photography and geology. And Geomon is the organisation. And they basically look after the rocks on the Isle of Anglesey. So anyone been to Anglesey? Very nice. Great place, isn't it? So all the rocks there are very, very special. In fact, Anglesey has got so much really interesting geology that UNESCO was like, okay, well, we'll protect it. You can't take a rock from Anglesey. Everyone's gone to the beach, picked a rock, take it home. Oh, that's not allowed. Don't tell me. Don't tell them. I would really. So that's really exciting. I get to be taught. I'm a field guide, so I can take a bunch of people, walk about, show them the rocks. And it's kind of like being a museum tour guide, but cooler. There's also an RMLI fundraiser, and that's me on the uniform. It was a very cold day when that photo was taken. Looks like I've got something in my eye. Probably did. That was really cool. Completely unrelated really to oceanography. Yeah, there's ocean, you're on the line with lifeboats. But that was just me talking to people, getting them to sign up, giving money. Pretty fun. Builds your confidence when you walk up to someone on the street and say, hey, give me money. Okay. It's really important to remember that it's not just the studying, it's the extracurricular. You learn skills that you might not get just from studying. You talk to people, you demonstrate. I can be a teaching assistant. I was an intern at one point, that's very fun. And without all of those skills, I don't think I'd be able to do what I do now. So, what is it I do? So this is a little screen grab of my dissertation. Don't even have to read it all. Don't even need to read the title. But basically, the internship that I took really threw me in the deep end of research. And my job was basically to trawl through all sorts of literature and research tidal dynamics in deep time. If anyone knows what that is. If you go to the beach, you know, the tide goes in, tide goes out. We're all familiar with that, yeah? Good. Nodding faces. That's good. What is my job then? Is I see the tide come in and out, but I have to quantify that. How do I quantify that? I need to say where the tides were, when they were, how big they were, how fast were they. And I do all of that with tidal sedimentology, the branch of geology. There's markers in the rocks. I get to read and figure out, tides did that. Ripples, you see ripples at the beach, they hit your feet when you walk. I look at ripples, I look at the geometries, the height, the wavelength, and figure out how fast the currents were when they deposited those ripples. I look at maps, paleogeography. I look at old tectonic reconstructions, I figure out where the oceans were. You all heard of Pangaea, old supercontinent on these bases? Yeah. Pangaea was around at the same time that I wrote my dissertation. Not that old. I wrote my dissertation on the time period when Pangaea was around, it was breaking up. Anyone heard of the Jurassic Park dinosaurs? Yeah. It was around the age, 150 million years ago. That's my first protocol. Got to say when the tides were, what they were doing. This in Europe. But also with my research, I get to do Milankovitch cycles. Anyone heard of that? Big word. It's the Earth-Moon orbit. So I get to learn about how close the moon was to us, the stood around hurtling through space. The Earth and the moon will eventually separate, the moon drift away. And I can figure out the rate, basically, of lunar recession based on my rocks. I just get to look at rocks and I know where the moon is. We slowed down from the Big Bang, but our days back then were pretty similar. But if you go back further and further and further, our days were pretty fast, like maybe 18 hours a day rather than 24. I can work out the length of day from my rocks. My research. Very cool. And I get completely thrown in the deep end by that. And in my second year, I thought, I like this stuff. Pretty interesting. So I did this for my dissertation. Which was that. During my dissertation, I really liked my supervisor, he was great. So I thought, what else can I do? What else can I do? I wanted to keep on with this project. I made in my internship a database. I took my data from like this one. And this database is shared between scientists here, there, and everywhere. So I'm in Oxford, Steve Baldus mentioned his name, don't know if people know him. He knows stuff about these tides. There's people in Portugal that I'm speaking to, people in Australia. All of these people use this database to find their information on these rocks, on these tides. Very interesting, and I wasn't ready to give up the project. So, what? So this is what I'm doing now. So I'm doing my MSc Res, which is a Masters by Research in rock music. You guys are going to hate me for this. You see these layers up here of these rocks? I'm turning those layers to individual tiny grains in an audio file. I'm going to play that file, and I'm going to figure out the rhythmicity in those layers. My audio is going to be rock music. Glad some people laughed, because this is the official, this is on the proposal for my funding. So some people liked it. So yes, tidal signals in carboniferous rocks. Well, the tide comes in, it deposits sandstone. And you see those layers, quite thick, quite sandy looking. Hope you understand. Lighter coloured layers in the rocks, those are sands. Tide comes in, deposits those sands. Tide goes out, deposits the muds, the darker bits. And I can see the individual tidal cycles. It's very exciting stuff. And I can't wait to turn it into rock music. Really, really annoy everybody when I say that. With that, I can rectify paleo maps. So what I mean by that is maps of the oceans, but millions of years ago. Very interesting. And my last thing, I suppose, and where I'll finish up, is that I'm developing a new type of method for these rocks. My method will read these layers of rocks in a way that nobody's really done before. And this is quite big for a little baby scientist like me. But yeah, very exciting. And I'm hoping I can do this for my PhD as well. So just take it from somebody that didn't know exactly what they wanted to do. You don't need to know just yet. If you do, that's great. But I think it's angler. That's me done. So,
And what Philippa said there is even later in your career, you still don't know what you're going to go. People move around in science a lot. My first degree was in theoretical physics. I spent a bit of time in my career in a company making electron microscopes and engineering, and now I use electron microscopes in material science. So you move around a lot. So Jim really illustrated how you don't know quite what's out there yet. That's what part of the network's about. This will help you sort of see what the options are. Thanks very much indeed. A few more set questions going to the STEM fair, I think. And then we're now going to have Miles, also from Bangor. We're getting a little bit tight on time. Yeah.
Sorry.
Not that much going on to say, so
Fantastic. Actually, linking back, Miles is going to give us tell us a little bit about Antarctic microplastics.
Yes.
So that's the plastics thing.
yeah. And in fact, the plastics being also interesting. So there we go. I didn't get any lectures on the beach, so a bit disappointed to hear about that. So yeah, my name is Miles, as you just heard. I'm actually a marine biologist, which means I do lots of science in the sea, kind of the opposite to what Jennifer does, where rather than the rocks and the sea itself, I just look at the animals and the biology that goes on there. I'm going to talk to you a little bit about my sort of pathway into research and how I got there, and I'll talk a little bit about my research as well. But I'll try and keep it short because I know that we are short on time. So how did I get into marine biology? Who am I? I actually started off on an access to HE science course at Sheffield College at 25 years old. So as we were just saying about changing careers, I know you're all at a point where you need to sort of pick a career for the rest of your life, but you actually don't. It will, if you're not stressed out by it now, you will be at one point, but don't be basically, because you can always change your mind later on. I then went on to Bangor University and I studied a Bachelor of Science in Marine Biology and Zoology. Did a whole bunch of internships and side projects with my lecturers, and if that's something that you are wanting to do when you get to university, just be enthusiastic and ask, and there's always cool stuff that you can do on the side. Quick show of hands actually. I know quite a lot of you guys are doing science. How many of you are maybe interested in doing marine biology, ocean science, anything like that? Is there anyone in here that's interested? Yeah, a couple of hands. Awesome. So now I've done my undergraduate degree. I'm in postgrad as an MSc Res, just the same as Jennifer. I'm still working on research projects with some of my old lecturers who are now just my work colleagues, which is weird. I'm helping teach in computer and lab sessions, giving talks like this, so quite busy. Yeah, so this is my my current office. It's actually just a histology lab that no one's using at the minute. So, like I said, I'm doing research, but what research is that? As we heard, I'm doing Antarctic microplastics, which is actually just microplastic in Antarctica, if anyone was wondering what that meant. Quite a few people think it's something different for some reason. And I've got two research goals, sort of two questions I'm trying to answer with my research. The first one is what's been going on over time with microplastics. Microplastics is kind of a new field, and I'm sure most of you already know, but just for those of you who might not, it is just plastics that have been in the sea for a long time and have broken down into tiny little pieces. But as a field, it's actually quite new, and we don't have a timeline at all for anywhere in the world, so I'll be producing the first timeline of that, which is really exciting. I'll also be looking at how microplastics end up in some of the bigger animals. If anyone's brave enough, does anyone hazard a guess as to how we think most microplastics end up in larger predators like sea stars?
In the water, fish accidentally swallowing.
Yes, accidentally swallow. Yeah, you actually got it right there. Quite a lot of people think that every fish with microplastics in it is eating microplastic. Actually, for the most part, the plankton are eating the microplastics, and bigger animals are eating them, and then bigger animals are eating those animals. We call the process trophic transfer, or maybe even bioaccumulation or something like that, you might have heard. I'll be looking into that a little bit because we don't know too much about how that works with microplastics. But yeah, these are my two research questions. And to do that, I'm actually going to be looking at an organism called Odon Plastibolidus, which is a sea star native to Antarctica. They don't have a common name, so we just call them oval, but they're just a sea star. They look very much like common sea stars that we get here. We're looking at plastic in the digestive system, specifically an organ that they've got called the pyrotica, which I'll get into what that is, but it's just a digestive organ that we don't have. But yeah, what's up with trophic transfer? What's the timeline look like? No one knows. I think that's the exciting part about being in research, is that I get to go out, find something that no one knows anything about, and answer the question. And when that question gets published and answered, it'll be, it's me that's done it. So it's really exciting to get involved in that sort of thing and like answering big questions like that. There's so many opportunities like that. So it's definitely interesting. It's a lot of fun, and you can always chat to all your colleagues about what research they're doing as well. So there's lots of that going on. But yeah, I think it's important. I won't go into this too much because I know I've not got too much time. But it's always important to have a why for what you do. And this is a really good time for you to think about why you might want to do anything that you do. But I just love the sea, and I care about it, and I think hopefully I can make a positive difference one day with my research. So the plan was to take questions and leave some of these quotes up. These are just some quotes from some colleagues of mine, and Jennifer's at Banger. I just asked some of them what they do and why they do it, but I think we're going to leave questions for the fair. Oh no! We're going to leave questions for the fair. We've got a stall up there. I've brought some sea stars for you to look at if you want to come some living alive ones. I think we've got some other displays, some of the chemistry displays as well. So yeah, come down and see us at the fair. It'll be really nice to see you all.
Thank you.